Okay,
Yes.
that's great. So thank you for the invite. So I'm Richard Worley from Queen's University. And so today I thought I'd spend a bit of time talking about MEMS wall-shear stress sensors. And these are some sensors we developed now over the past few years, and we've had a couple of patents out protecting these types of sensors. And an image of them is here. And so they're a small square die, typically 5 mil by 5 mil. And then in the middle here we have our sensor, and we have some kind of sensing pad that we mount flush onto aerodynamic surfaces like aircraft wings, aircraft fuselages, or even in wind tunnels for wind tunnel testing. And we use these sensors to directly measure wall shear stress, or ultimately skin friction drag, viscous drag across aerodynamic surfaces. So I thought just to open up, I'd explain the driver for the research and the reason why I started developing the sensor in the first place. And so in terms of aerospace applications, if you had an aircraft flying at cruise, if you could reduce the drag experienced by the aircraft by just 3%, you'd save around £1.2 million in jet fuel per aircraft per year and prevent the release of around 3,000 tons of carbon dioxide per aircraft per year. And there's currently around 23,600 aircraft in active service, and so it becomes a £1 billion problem for the aerospace sector. And so the ultimate end goal is to develop a technology stack for transport decarbonisation, energy reduction, using turbulence controls. As the flow moves over the aircraft, you've got this turbulent flow that generates this turbulent wall shear stresses, which move all the way over the aircraft. And the idea is, can we come up with a way of controlling the turbulence? And if we can, we then need to have a sensor to detect that our control has been successful. And that's where these sensors have come about. So to give you an idea about how complex a turbulent flow is, I thought I'd just show you a video of a simulation of flow over an aircraft wing. So I'm just going to I'll break this session here and just move over to another screen. And hopefully you can see this other video playing. Can you see this video? Can someone give me a nod?
Yeah, we can.
You can? Okay,
Yes, yes.
brilliant. So this is some simulations that were done at KTH over in Sweden by Schlesser's group, and these are really high-end simulations. They're going to zoom in and just take a look at a really tiny area of an aircraft wing, and you'll get an idea of the turbulence which is flowing over the aircraft. So I'll just play this through. There's no sound on this one. So we're going to zoom all the way in to a little tiny area of this aircraft wing, and then we're going to see some simulations of the turbulence that moves over this aircraft wing. And so what you get is something like this. So flow is now going into the plane of the paper. And when you go away on holiday and you're in your aircraft, in your airplane, obviously you can't see the air, but there's all these turbulent structures. They look like little horseshoes moving along and down the flow. And ultimately, these horseshoes, like quasi-streamlined vortices, which rotate like this, and they drag all the high-speed fluid from the outside of the aircraft in the free stream, and they crush it into the aircraft wall. And it's that process, that downwash, that generates a skin friction drag. And around 50% of the total energy consumption of the aircraft is due to these types of structures, which are dragging the air and crushing it into the surface of the airplane. And so ultimately, we want to try and work out a way of trying to control this turbulence. And if we can, then we need the sensors to detect when control has been done successfully. But as you can see, it's a very complex flow with a range of different scales, and these different scales have spatial scales, time scales, and velocity scales. It's a very, very complex type of problem. And ultimately, I'm going to skip through a little bit now, a little bit further on. But ultimately, our sensors would sit underneath this blue bit on the surface. And as the airflow goes over, we then pick up on these instantaneous fluctuations of forces which these structures impose on the aircraft surface. Okay, so I'll just return back to my main presentation. And hopefully that's come back up again now on here. And hopefully what that illustrates is it's just that wall turbulence is very, very complex, and there's a wide range of length scales and also time scales involved. So why do you want to measure wall shear stress? Well, I've explained there's both fundamental and practical importance. The practical side of things, if you can control wall shear stress, then ultimately you're going to save lots and lots of money. You're going to reduce emissions, etc. So great practical importance. But also from the fundamental side, there's lots that we don't really know about wall shear stress and wall turbulence. And so if we can try and discover new things about wall turbulence, then potentially we might be able to then exploit those new physics to control wall turbulence. And so that's one aspect in terms of the fundamental knowledge, but also in terms of the CFD, so computational fluid dynamics. If you want to try and develop some new models for high-speed aerodynamics, for designs of, say, new aircraft, what's vitally important is to know what's going on along the boundary of those simulations, which is where the wall shear stress comes in. And it's very difficult to take these measurements of the wall shear stress in these types of high-speed flows. And so one thing I'm particularly interested in is developing active control techniques. It's seen as an upstream technology enabler, which is yet to be exploited. And if you can have a sensor which ultimately can measure the instantaneous stress or the instantaneous footprint of the turbulence, then maybe you're opening up enabling pathways to control that turbulence too. However, trying to capture this instantaneous fluctuating wall shear stress is very, very difficult. And there's been a fair few different people that have tried. We've got some floating element types over here based on a capacitance sort of technique. These floating elements, they're flush mounted into the wall, and these elements can be quite large, like 1 mil by 1 mil, based on capacitance, so there can be quite a lot of drift. And there can be some issues associated with things like EMI, all the way through to things like micropillars, where you have this little tiny pillar which pokes up from the surface. So this would be the aerodynamic surface down here. And as the flow goes over, this pillar will begin to bend back and forwards and move around in the turbulent flow. And these have been shown to work quite well in liquid flows. However, there's some constraints. And if you try to use these in airflows, for this to be valid, this entire structure here would have to lie within something called the viscous sublayer within the turbulent flow. So very, very, very close to that wall on that video that you just saw. To put it to context, if you're in a wind tunnel, I'd say a modest 10, 15 meters per second, the height of the structure would have to be around 100 microns or less. And then if you scale that up to an aircraft, this would have to be more like 1 to 10 microns. And it's very difficult to find a structure which has the compliance to move around at that sort of time scale and that sort of length scale as well. So very problematic to scale these things up. And then you also have some commercial probes available from people like Dantec, who sell these hot film probes, where these are flush mounted into the wall and you have a heated element. And ultimately you keep this structure here on the front here to around, let's say, a few hundred degrees. And then you measure the convective heat transfer away from that surface and calibrate that back to wall shear stress. But the problem is with these sorts of devices is that you're also heating up the substrate around the sensor, and that can dampen all the fluctuations out. So although you can get the mean wall shear stress, you can't get the fluctuations very well. And so we decided to try and make some MEMS sensors to try and fill these gaps. And our first aim was, can we develop a sensor which can measure instantaneous wall shear stress and direction of the flow. And so direction of flow, I call that the streamwise direction. And if we can do that, can we also then develop a sensor which can measure two components of the stress? Stress ultimately has multiple components. And so because we know we've got these vortices rotating around, can we do the streamwise direction, but also the spanwise direction as well? And if we can do that, can we then develop arrays where we can then have sensors mapped out over a surface? And so we can track the turbulence moving over aerodynamic surfaces. And ultimately, if we can get a working sensor, can we get that into a wind tunnel and then benchmark it against some other form of indirect measurements of stress? And then ultimately, the end goal is flow control applications and deepening our understanding of flow physics, and i.e. having some kind of feedback control. So, why MEMS? Well, turbulence is a wide range of spatial scales and temporal scales, and so there's a possibility of all those being resolved by MEMS sensor technology. It's possible to have a sensor die which is flush mounted into the aerodynamic surface, so it's hydraulically smooth, it's not intrusive, it doesn't start tripping the flow or causing issues with the flow. And it's possible also to do direct measurements, which is very attractive. There's also scope for implementation of sensor arrays across the surface. And then, interestingly, with using a MEMS technology approach, we could potentially develop a sensor or a chip which has multiple sensors integrated in one go. And so maybe we could measure wall shear stress, but also static pressure. And so we can start getting gradients of stress and also local pressure gradients simultaneously, which would be very advantageous. And so for us, we've used an optical approach, and we did that because we wanted it to be robust to things like EMI. And we found we've taken this approach. We're good in terms of water ingress. We also wanted it to be used in both conductive flows and in liquid flows. Although we've only tested it really in air flows, I'll show you some robustness tests that we've done so far. And we wanted to avoid any electrical sensor, any electrical connections on the sensor as well. So if I fast forward, our sensor system looks a little bit like this. And so we've got some background electronics, which we've developed. I'll talk through that shortly. And in the end, we end up with this bit here. And so this cylinder, ultimately, this surface here gets flush mounted into the wall of, say, a wind tunnel, aerodynamic surface. And the little square piece here on top is our MEMS sensor. So ultimately, we can calibrate these things. So they come pre-calibrated. We just install them into a wall, plug and play approach, and we can start measuring directly instantaneous wall shear stress. So how do these things work? Well, if we take a zoomed in view of our sensor, one sensor type is what we call a clamped design. And so here we have a floating element. And so typically this element here is a few hundred microns by a few hundred microns, and it's suspended by these 4 microsprings. And so as the flow goes over, we have some stress or some force on this floating element, and it's free to move back and forwards in plane along the surface. And if we took a look at some of the dimensions and we applied some beam theory based on the dimensions on things like Young's modulus, etc., thickness, we can work out how far this thing's going to move based on how much wall shear stress tau we apply over our sensor. And then we have another design, we call it a serpentine design, where now you've got this spring which moves back and forwards like a serpentine effect. And again, we can use beam theory and we can work out how far this sensor is going to move theoretically under a given applied wall shear stress. And this one's quite interesting because it gives you basically more sensitivity. Although it's harder to make, it does give you more sensitivity for the same wall shear stress. So how do we detect this motion? So you could technically look at this thing moving with a high-speed camera, but it would be very, very expensive. And so what we do instead, we use something called Moiré fringe transduction. And so we end up with ultimately 2 sets of gratings. One set of grating etched directly onto the silicon die, and then another set of gratings against a piece of glass underneath. And then as the sensor begins to move, the gratings on the silicon begin to move with the sensor, and the glass remains stationary, and then we end up with this fringe pattern which begins to move. And so we did that because as you superimpose 2 sets of gratings, we generate this Moiré fringe pattern, which has some bigger gratings, say G, and ultimately end up with an amplification factor. And so, for instance, if our sensor was going to move, say, 1 nanometer in the flow, the Moiré fringe transduction effectively boosts that by a factor of, say, about 100 typically in our types of designs. And so it's easier to see that type of motion. So we've got a bespoke manufacturing process. We end up with a soy wafer. We go through a series of different masks, and ultimately we etch the structure into the silicon. And here's some images as I step through. This bit now is with the gold grating going on to the clamp design or into the serpentine design. And there, there's one set of gold gratings that are directly onto the silicon section. And then ultimately we get some glass and we bond some, so we etch on some more gratings onto our glass, and then we ironically bond the silicon and the glass together, and then we end up with our sensors. And so if you take a look back and just squint a little bit, you can kind of see on this sensor here the dark bit and the light bit, and that's the Moiré fringe pattern that you can see. This is the serpentine design. And at the bottom here is some arrays that we developed, although today I'll talk more about the 1D sensors up here. And so ultimately we end up with a wafer, and then we chop that wafer up into our sensor dies. And so if we take a look at one of the sensors, our clamp design, here's an SEM image. Ultimately, flow would move from left to right. Here's our floating element. Okay, so the flow goes over, apply some stress, and that floating element begins to move back and forwards in a turbulent flow along the wall of the aerodynamic surface. And ultimately, you can see the more fringe patterns here, the light and the dark bands. And if we take a zoomed in view, this is our micro spring. So typically at around 7 microns, typically in our types of sensors. And if we take a look at the gratings, these gold gratings typically around 3 to 4 microns with a slightly different pitch to generate that fringe pattern. So if we take a zoomed in view of the gratings, and this is an SEM, you can see all these vertical lines of the individual gratings. And then in the background of that, you take a strike through the middle, you can kind of see the dark patch, the light patch, the dark patch, the light patch, and that's our moire fringe pattern there. So if we take a look at this SEM, the blue lines are the individual gratings, and then the black line through here is the sine curve of this moire fringe pattern. And so the way that we track this motion is rather than using a high-speed camera, we get a series of LEDs, we launch them down a fiber optic cable through a lens array, and then we essentially sequentially ripple the LEDs very, very quickly on the back end of the sensor. And so LED light comes in, hits the back of the sensor, and then bounces off and gets picked up by a photo detector. And we ripple the LEDs through at very high frequency, much higher frequency than anything within the flow. And so ultimately, one line scan through the back of the sensor is quick, is so quick, the sensor hasn't even moved until you get an instantaneous snapshot of what's happening at the back end of this sensor. And so these black dots here are the response from the LEDs hitting the back of the sensor that's picked up by the photo detector. And so ultimately these lie on this sine curve here. And so ultimately, as the sensor begins to move, those dots begin to move. And then what you're tracking is that sine curve moving back and forwards with time. So ultimately, if we take a look at what the package looks like, here's our sensor that mounts on the top here of our package. And then we launch the LEDs in through an MTP adapter. They get focused down by a lens array, typically to around 10 to 15 microns. They go through a beam splitter, hit the back of the sensor, back, and then through 90 degrees into a photo detector. So once we've got our sensors, we then need to calibrate them. And so what we built up was a laminar channel flow facility. And we did that because ultimately, if you get a very high aspect ratio channel flow facility, so typically ours has a half height of around 250 microns. And ultimately, if you measure the streamwise pressure gradient, you've got a direct measure of the mean wall shear stress. And so ultimately, we would then mount our sensor within our channel flow facility, take a measurement of the pressure drop across the channel, and then from that, we've got our measurement of our wall shear stress that we need to calibrate our sensor. And so in terms of the fluid dynamics, if you plot the friction factor against Reynolds number for a high aspect ratio channel flow facility, it should be this straight line here. And so nice little our data lies on there, so we know our channel flow facility is working well. And so if we take a look at some of this data, the blue line here is the sine curve in the back of the moire fringe pattern. We've now got no flow on. Okay, we're just sat in the channel flow facility. The black dots are the response back from the photo detector. And then as I put the flow on and I apply a force to the sensor, ultimately what you should be able to see here on this inset is this sine curve begins to move further over and to the right-hand side. And so as I apply more force, the sensor moves over to the right-hand side, and we start to get this pattern of all these different sine curves moving over to the right-hand side. And so ultimately from that phase shift, we can then plot out the displacement of the moire fringe pattern against the wall shear stress from our calibration facility, and we get a nice straight line for our calibration curve. And so think back to the very start of the presentation, I showed you those analytical framework of how far this sensor should move analytically. And if we just plot that on, we get the red dashed line here. And so we get really great agreement between our analytical framework and our experiments. So we've got a very good idea about how our sensor is going to behave before we decide to put this into production. So next, we also do some dynamic calibrations too. And so what we do now is we take the sensor die, we place it on a piezoelectric shaker, and then we shake it back and forwards at a range of different frequencies. And so a couple of videos here that you should be able to see the sensor moving back and forwards, and you can just see that spring within that gap here. And ultimately, again, we've got an analytical framework. And so here, the black line is the data from the experiments, which shows resonance on the left-hand side around 2.64 kilohertz and the right-hand side just over 4 kilohertz. And then the blue dash line analytical framework. And so again, great predictive capability. We've got a very good idea about how these sensors behave before we decide to put these into production. And so we also then, after we calibrated these things, got them into a wind tunnel. And so what we had is a 3 meter long wind tunnel with a 3 meter long flat plate. And then we tripped the flow into a turbulent regime. And so a bit like what you saw in that video at the very start, you have all these turbulent structures moving down across this 3 meter long flat plate. And then we placed our sensor into the wall. And what we had was a laser-based system, something called laser Doppler velocimetry. And it has two intersecting laser beams. And if you place the LDV within the viscous sublet, it's a very difficult measurement to take, but you get an indirect measurement of the wall shear stress because you measure the streamwise velocity gradient effectively and then invoke the stress from Newton's law of viscosity. And so what we have with the LDV directly above the sensor is instantaneous wall shear stress with time in blue. And then next, if I now just plot on the data from the sensor, we get the red data. And so we've got really good agreement between the LDV and the MEMS. Now, as soon as you increase speed a little bit further upwards, the viscous sublet becomes so small you can't get the LDV in there anymore. And so in which case is why you permanently need the MEMS sensors. But ultimately what this is showing is great agreement between an indirect measurement and then also from the MEMS and capturing all of those turbulent structures very, very nicely. And so we then also looked at some statistics over 3 different wind speeds, so quite low speeds of 6, 8, and 10 oncoming speeds. And if you plot out those fluctuations, those PDFs, we get great collapse between the laser-based system and the MEMS sensor. So ultimately, things are working really well. So we also tested for some robustness, and so we wondered what would happen if our sensors come into contact with things like water. And so what we found, because silicon's hydrophobic, if you put some water on there, it just balls up, and then we get no water falling down between that gap between the silicon and the glass. We also turned it into a block of ice, but again, we defrosted it and the sensor worked well, so that wasn't too much of an issue. We simulated rain, and again, the sensor carried on working well too. And then what we also did, we tried to then force water in between the silicon and the glass. And so I'll just show this video here. And so now you should see, there we go, water's going in. And I thought, okay, the sensor now must be broken because we've forced water into that cavity in between the sensor and the glass. However, because there's only nanoliters of fluid, a fraction of a time later, all the water just simply evaporated and we had a working sensor again. So it seems quite robust to things like ice and also water. And so we've got quite a few different sensors fabricated up now. We've typically calibrated them to around 5 pascals, accuracy around that 1.5% sort of mark, resolutions of 10 to 100 micropascals, and hopefully next round of fabrication underway shortly. So conclusions for now. Well, we successfully developed these MEMS sensors for direct measurements of instantaneous wall shear stress. So we've got a new capability for the fluid dynamics community. They're typically accurate to around that 1.4, 1.5% mark. Repeatability is around 0.7%. And we've got resonant frequencies up to around 8 kilohertz, but it depends on how you design the sensors. We've got patents now protecting these sensors back in 2022. Our smallest floating element size is around 150 microns by 450 microns, but ultimately we'd like to go smaller than that if we could. We've now got some nice robust approaches to statically and dynamically calibrate the sensors. So ultimately the sensor can be provided pre-calibrated. And we've got a very good idea about how our sensors will perform before we put them into production because of the nice analytical approaches that we've developed. They seem quite robust to ice and water, so promising for field experiments. And then ongoing, we're now looking at developing the sensors for those two components of instantaneous wall shear stress, the streamwise and spanwise wall shear stress simultaneously, and also packing these things into tightly knit arrays, something like 100 sensors within a single 30 mm diameter. So there's more on the horizon, and so over the next year or so, Boeing should be developing a half model like this, which should be coming over to the National Wind Tunnel facilities in the UK. And we're currently working with Boeing to make sure that this type of model has the right infrastructure, and so we can place our sensors and also our actuation systems onto a model like this and get this into the National Wind Tunnel facilities. And so we have more of a realistic aerodynamic body to do some testing onto. So we're also exploring some new problems where our sensors could be used. And so just to finish off, I'll play you a short video which kind of explains the aviation sector a bit more about what we're trying to do with our sensors now, and also how we're trying to move over into the space sector and also into the biomedical sector as well.
Scientific breakthroughs often begin with a paradigm shift, like the ability to measure something that no one could measure before. At New Solutions, we've created ultra-sensitive, ultra-miniature sensors that can measure instantaneous surface forces so small they've never been measured before, until now. We're unlocking game-changing possibilities across multiple industries. In aviation, we can capture the instantaneous viscous drag across wings and fuselages directly. The payoff? Smarter aircraft design, better fuel efficiency, lower emissions, and real-world validation for simulations of the future. In space, we're redefining gold standards on how microthrusters are tested on Earth, and eventually, real-time thrust monitoring onboard next-generation small spacecraft, all to enable the space innovations of the future, including the precision pointing of microsatellite constellations, in-orbit refueling and servicing, and even asteroid mining. And in biomed, our sensors could accelerate the next generation of surgical tools designed to reduce the force on the retina during delicate procedures like vitrectomy. That means safer surgeries and better patient outcomes. We're building the technology to sense what's never been sensed before. No more indirect measurements, no more not knowing. If you're working in aviation, space or biotech, please get in touch. New Solutions. Direct, instantaneous, ultra-precision sensing.
And then finally, just to finish off, it's not just me developing the sensors, we've got a team of people working behind the scenes as well. And so all these people on the screen have been instrumental in developing the sensors you've seen so far. And that brings me to a close. Thank you very much.